Hello, everybody. My name is Oliver, and I work in the numerics group for Wolfram Research, and I mainly work for on implementing the finite element method and partial differential equation models. There is a web page, one of the core area pages about the finite element method that gives a nice overview of then capabilities that we currently have. So if you want a more general overview than this presentation, that's a place where you could start looking at. I'm going to present new capabilities that we've added in 14.1, and I'm going to give a short overview of these new features. Before we dive deep into that, I'd like to point out the PDEModels Overview. This is probably the most important slide in the entire presentation. And the reason is that the PDEModels Overview page has a large collection of examples, monographs. Basically, this is the starting point if you want to implement partial differential equation models. So we can have a brief look at this. So this is the PDEModels Overview page. It has some introductory text, and then you'll find things like different fields of physics, acoustics, electromagnetics, fluid dynamics, heat transfer, mass transport, multiphysics, and things like that. Solid mechanics is also there. Yeah, so this is a nice overview of what capabilities we have. These sections are structured in the same way. You'll have the functions that generate the PDEs and their corresponding boundary conditions. So for example, for heat transfer, we have a heat transfer PD component. There's monographs, there is application models that you can look at. And here is a models overview. It says, so for example, the heat exchanger, it's a 2D model, it's transient, is a coupled model, and things like that. So you can find specific application examples that may be useful for your own partial differential equation modeling. Okay, so that's a brief overview over that. Now let's have a look at what we've added in version 14.1. So we continue to extend the electromagnetics section. There's new components, and we'll discuss them in a second. We've updated solid mechanics, and we've also updated the Schrödinger PD component. There are also updates to the Open Cascade link. However, I'm not going to present them here today. The main addition that we've added here is that you can now use Open Cascade link to do 2D drafting. That means you can take 2D graphics primitives and then put them into Open Cascade, do some operations with them, like Boolean operations, and then get them back to Mathematica, or you can extrude them to 3D objects and things like that. So you can work in 2D and extract that and then use that for a 3D model. Okay. So electromagnetics, there are two new monographs. There's an electromagnetics overview monograph and an electric current monograph. The overview monograph is basically an overview of electromagnetism. And the main idea here is to give some guidance on what equations to use in what scenarios. And we'll talk about that in a second in more detail. You're going to see a slide about a decision diagram, how to do electromagnetics modeling. And if you're curious about that, you can have a look in this monograph. This is the diagram we're going to look at just now. And this is going to be explained in much more detail in this monograph than I can do this in the current presentation. And the second monograph that we've added is about electric currents. So we're going to have a brief look at that. And that's basically introducing a new PDE component that's used for electric currents. So again, lots of application examples, ideas how to model, how to use the operators and things like that. All of that can be found in this monograph. Right, let's have a look at a few examples. So for the electromagnetics overview, basically the idea is that we have Maxwell's equations, and the problem with Maxwell's equation is that if you want to solve the full Maxwell equation, it's very resource intensive. So computational time, computational memory are quite expensive to compute the whole thing. And you're always looking for simplified equations that are based on some assumptions. So you'd like to find the simple case that represents the scenario you want to model. And that's what we've tried to help you with by adding a decision diagram. So for example, for electromagnetic modeling, the first question you should ask yourself, is this a transient, saying a time-dependent equation or not? No, that means the electric field and magnetic field are, the time derivatives are zero. Then do you only want the electric field, only the magnetic field? If we only have the electric field, then depending on one constitutive relation you have, you can use the electrostatic PDE component or the electric current PDE component. And the same is true for the magnetic counterpart of it. So we have a magnetostatic PDE component that's introduced, and we're working on a magnetic PDE component that's going to be introduced in the future. So for a transient case, you'll have a look and see whether the length of the object is much, much smaller than the wavelength you're looking at. Then we are in a low frequency domain. Then you'll have to consider the skin depth. If the skin depth is much larger than the object, then we get away with simulating the electric field only. And for that, you can use the electric current PDE component that we've introduced in this version. And so on. So this is some guidance of what functions to use in what scenarios. Okay, electric currents. So this is basically the equation we're looking at. We've added examples, an entire monograph. So the new function is the electric current PDE component, and there's a new boundary condition, current density value. This application, this model can work in 1D, 2D, 2D axisymmetric, and 3D cases. We have stationary and frequency models. And one thing that is still missing that's coming in the next version is a time domain. So we don't have that yet, but we're working on that. So, but we can still make useful things with this as is now. So here's an example. So we have a geometry here, like this wire that's bent a little bit. And what we're going to do next is we discretize this. So this is the discretized version of this wire. And now we're going to set up the variables. So we have a potential. It's a three-dimensional case, x, y, z. And we select the material tungsten, and we generate the electric current PDE component. So that's the equation it generated for us. We set boundary conditions. So on one edge, we have an electrical potential of 0.2 volts, and we have an electric potential of 0 volt because you haven't specified any electric potential for this boundary condition. That means the default is 0. So we have a 0.2 on one side and a 0 volt potential on the other side of the wire. We can feed this to NDSolve. NDSolve will then return an interpolating function with the solution, and we can now visualize this. So we compute the field, the gradient of the potential gives us the field, and visualizing the total square of the field in the square root gives us a nice overview of what's happening here. And it's interesting to see that there is more current flowing on the inner boundaries here than on the outer boundaries. Just I thought it was a nice example to show. Right, so that's basically the current density vector visualized. There are other examples, of course. So here, what you see in these top two visualizations is we have a wire in an old light bulb. So we see the current flowing, and we can actually then couple this with the heat transfer equation and compute how hot the wire is getting in the light bulb. This second example below here is basically modeling a capacitor. So you see the charging and discharging of the capacitor model as a full finite element model. Right, so these are a few other examples. For solid mechanics, so we're changing gears a little bit. Solid mechanics, we added a new function, von Mises stress, and the goal is to compute the von Mises stress of a deformed body. The problem is that in solid mechanics, when you deal with stresses, the stress tensor has 6 components, and it's quite unmanageable to work with that. And the von Mises stress is a way to combine these stress components into a more manageable expression. All right, let's look at an example. So we have a geometry, that's this geometry here. We have variables and parameters. So we have u, v, and w. Those are the displacements in the x, y, and z direction. X, y, and z are the independent variables. And as a material, we choose titanium. So this is a titanium object. And we proceed as normal with, for a solid mechanics PDE component that generates the equation. We set boundary values. So on the right edge, we have a force of -2⁷ in the negative z direction. And on the left-hand side, the beam is held fixed. We then compute the displacements with NDSolve. Nothing new here. And we continue to compute the strain from the displacement, and from the strains we compute the stresses. So now we have this stress tensor. We see it's a 3×3 matrix, and you can extract a single component. So the sigma yy component is the 2,2 component. So that's the interpolating function representing this stress here. Now, what von Mises stress does is it takes this stress tensor and combines this into a single expression. So this new function von Mises stress takes the vars, the variables, the parameters, and the stresses that we've just computed and computes a single expression from this. This is the von Mises stress. So, and here is a vector displacement of the displacement and the von Mises stress plotted on top of it. Now, what do you want to do with this? So, the von Mises stress is useful to figure out if a material has been pushed beyond its yielding limit. So for the material that we had, we used the tensile yield strengths, and that's 10 to the 8 roughly for this specific material. And now we can write a function. If the von Mises stress is larger than this limit, then we want to have a 1 as a result, and if it's lower, a 0. And now we can visualize the areas that are subject to failure because we've pushed this deformation beyond the yield limit. So displacement, again, the vector displacement plot of this displacement and the criterion. So you see these yellow areas, that's where we suspect that the material will yield, and that's obviously not a good thing to have for this specific case. So you'd have to reduce the load a bit, or do reinforce it, do other things to deal with such a high load. All right, so that's that. Another new, again, we're changing gears. Another new addition has been made to the Schrödinger PDE component. And the update here is that we want to be able to compute the time evolution of wave packets under the presence of magnetic vector potentials, and at the same time have a non-isotropic effective mass. And this then can demonstrate the Aharonov-Bohm effect. Yeah, it's just an addition, an extension. We'll see this just now. All right, so we set up the variables and the parameters. So it's a time-dependent problem in 2 dimensions. And now in the parameters, we see we have an anisotropic mass of the electron particle, and at the same time we have a magnetic vector potential. So this is the new thing, that you can combine these two components, so to speak. Right, so here the Schrödinger PDE component is set up, and this is the solution. I mean, I've the actual code. If you're interested, it's there. There it is. So there is the actual code now, and we can look at the result here. So that's the code. Didn't want to go into too much detail here, but we can look at the result. Right, so there, now we have the wave packet that's hitting this slit, And this is the magnetic interaction that's set behind it. And we see it slightly asymmetric now. All right, so that's a new functionality for the Schrödinger PD component, right? We've added new application examples, and I'm going to present a choice of a few of them. I just tried to take a few from different areas. Right. So the first example, and all of these are links, so you can actually look at them in the documentation. So this is a thermal contact example. Yeah. So what we have here is a modeling of a thermal contact that has a discontinuity here. So the thing is heated here, and there's a small, very minute gap here, and then there's a second component here. So this is a material, this is a second material, and they don't quite touch. So there's a discontinuity here. And you can see in the resulting temperature plot that we can now nicely handle this temperature gap here. So that's one example I wanted to share. We've added an electrostatic case that's coupled to solid mechanics. So here we have an electrostatic field, and that field is driving a deformation of this cantilever beam. Again, yeah, if you click on the link, you'll see the example in the help system, and you can have a look at the exact details of this. And the last example is that we've added a way to compute a non-Newtonian fluid, and this is a cerebral aneurysm. So what we have here is the artery, and here's where the aneurysm formed, and we see how the fluid flows in this aneurysm. We're planning to extend this a little bit further, but that's for the upcoming release. But again, this is modeling blood with a non-Newtonian fluid flow model, right? Another example is an axisymmetric quantum dot. And this is an analysis of single particle states that are confined in a semiconductor quantum dot. So if you're into physics, that's probably an example that might be interesting for you. All right, so what's the future of PDE modeling? So we continue with electromagnetics. So the next thing on the agenda then for a future version is magnetostatics. To flesh that out a bit more. And we're also working on plastic deformation. So for solid mechanics, we'd like to do things that happen when you go beyond the yielding limit of a material. That's why we introduced the von Mises stress. What happens if you do actually go beyond this deformation? We want to be able to model that. So that pretty much concludes my presentation for the updates for 14.1. Again, go to the web page or go to the PDEModels Overview page. There's lots of new stuff there that you can find there. I think NDSolve is the coolest function, of course, and I thank you for your attention.